All right, this video is going to go over pages 15 through 17. We're going to talk a little about amplitude and reflections on this one. So remember, amplitude is, when we talk about waves, we talk about a transfer of energy. It's not the transfer of particles, so it's not one particle starting at the beginning of a wave and going all the way to the end. It's the transfer of energy between one particle to the next. So one particle can stay in place, and what happens is it vibrates up and down or side to side, and that'll transfer energy to the next one, and then it just kind of keeps going and going. But that original particle is still where it was. So amplitude is the amount of energy in a wave. So basically how loud it could be, how big the wave is. Okay, so our example would be like a tidal wave versus a small ocean wave. A tidal wave is very destructive because it's a very big wave. It has a lot of amplitude, okay, a lot of height. Okay, versus a small ocean wave, not much there. Or loud sound versus soft sound. So like amps, when you think of when you hook a guitar into an amp and stuff like that, that can control how much amplitude is happening. Okay, so that can determine how loud you want it to be or how soft you want it to be. Okay, so two waves can have all the same properties. Okay, so they can have all the same properties. Okay, frequency, wavelength, and velocity, but still have different amplitudes. So the key thing here is just because we change the height of a wave doesn't mean we need to change everything else. Like I've seen some people where like if I said decrease the amplitude, they think that means you stretch the wave out, and which makes it longer, which was going to change your wavelength and change your frequency, but that's not the case. Okay, you can make it as high or as low or as low as you want. Okay, without actually affecting the frequency, wavelength, or velocity. Okay, so just make sure you understand that, so you can have different amplitudes, but everything else stays the same. So I even drew an example right here. Okay, you have your red wave that definitely has a higher amplitude. So you see how it's going higher. So it's almost to like a 1 here. Okay, probably could draw this one a little bit further down. Okay, -1 down here. Okay, so your amplitude is a lot higher for the red than the green, but if you look, they have the exact same amount of waves. Okay, the same wavelength, same frequency. Okay, doesn't mention any change in velocity, so you can have all those same properties, but you can change amplitude any way you want to. Now, if you want to talk about losing amplitude, that's a term called damping. Okay, damping is a decrease in the amplitude of a wave over time due to loss of energy. So energy lost due to friction. Now, that could be things like friction due to air, like water and stuff like that. If you run into ground, things like that, that's naturally going to slow things down. So that can slow the energy down, but it's not going to actually slow the velocity of the wave down. Okay, so you can reduce the energy or reduce basically the pack or the punch of the wave, but the velocity can stay the same. You can make the wave smaller, but the velocity is still going to be the same. So it'd be like taking like a tidal wave and reducing it to a little wave. Okay, but it's going to have the same velocity. Now, as a wave travels away from the source, its amplitude decreases, but its velocity remains constant. So this is a key term here. Okay, the loss of energy is shown through a decrease of the loss of energy is shown through a decrease in amplitude, not velocity. So you can change the amplitude all you want. The only time you can change the velocity of a wave is by changing the medium itself. Okay, if you have a wave in water and it stays a wave in water, it can only move so fast. Okay, so water can only move, it's just that type of medium. So an example would be like sound. Okay, so sound can move fast. Okay, so roughly in air, it can move about 340 meters per second. In water, it actually moves 5 times faster. Okay, so that's the only way you can change the velocity of sound is if you changed it from a different medium. Okay, so if you had sound in air and you wanted to go faster, you can only make it go so fast in air. But if you wanted to go faster, then you can introduce it to something like a liquid or a solid where you're changing that medium up. Okay, and that will allow you to increase the velocity. Now, when we talk about waves that are sent down, we're going to talk about reflection. So reflection happens when we send a wave down a medium, and that can either hit a fixed end or a free end. Okay, so what a fixed end means is something's holding something holds the medium in place at the other end of whatever the medium is. It could be a rope, could be a string, anything like that. But the point is that both ends are fixed. Okay, versus a free end. A free end is where the end is just free to do whatever it wants. It can go up and down however it needs to. Okay, so I drew an example here. So we're sending a wave down. This is called our incident pulse. So our incident pulse is the one that's incoming. So incident pulse. Okay, it's going to hit that fixed end. Okay, so when I think of a fixed end, so this is our fixed end right here, meaning the end of that rope is not going to go anywhere. It's going to stay attached to that fixed end. So the way I think about this is an obstacle. Okay, it wants to move freely, but it can't. Okay, so that means what happens is the reflected wave, so when the wave comes back, it's going to run into that obstacle and it's going to become inverted. Okay, so our reflected pulse right here, the one that's coming back, that's what a reflected pulse is, okay, is inverted now. Okay, so when it comes back, it's going to be inverted because it hit that fixed end, it interfered with its motion. Okay, so it's going to send it back the opposite way. Didn't change the wavelength, frequency, anything like that. Didn't change the amplitude, it just changed the direction of the amplitude. Okay, so instead of having a positive amplitude like up here, now you have a negative amplitude here, so that's considered inverted. Now, if you send a wave down, okay, so you send an incident pulse down towards a free end, so like right here, that would be a free end, so nothing's inhibiting its motion at all. Okay, what's going to do is it's going to hit that end and come back the same way it was. Okay, so it's going to come back upright. Okay, so same amplitude, same all that stuff. Okay, it's going to come back the exact same way it came, and that was at the free end. Now again, so this is more of a drawing about a free end, so you could see something like this where you have like a string attached to like a little ringlet, okay, and that ringlet is allowed to where this rope can, this little ringlet can do whatever it wants. It can go up and down. It's not really hindered. Okay, so that would still be considered a free end, so your reflected pulse would come back upright. Now, going back towards a fixed end, okay, so a fixed end is where the end of this rope, like right here, I'm gonna use a different color, right there, it's not going anywhere. Okay, so that'd be like someone else holding the other end, it's not going anywhere. Okay, so once it hits that fixed end, that reflected pulse is gonna come back inverted. Okay, so just make sure you know when it's gonna be upright and when it's gonna be inverted. And that's basically the gist of this video. There's not a whole lot to this one, so just make sure my key takeaways are, know what happens when it hits a fixed end. Okay, so is it gonna come back upright? Is it gonna hit inverted? Okay, know what happens when it's gonna hit a free end. Okay, is it gonna come back upright? Is it gonna come back inverted? Okay, and then make sure you know that your terms for amplitude, damping, how you reduce that energy. Okay, and that'll be the gist of this one.